Okay, so as we talk about domain on 5 and 6, okay, so there's two things I tell you guys to watch out for in domain when you look at the equations. What are the two things I tell you to watch out for in domain? Right. So we have to consider square roots and denominators. Denominators. Okay, I should have abbreviated. Now, as we look at number 5, what do we have in number 5 we need to be concerned about? There is a square root, right? And as we look at this square root, any value under a square root must be what? Has to be positive, right? So whatever you have under your square root, in this case 12 minus x, we're going to take that and set it greater than or equal to 0. Because we want whatever is under that radical to be greater than or equal to 0. We want it to be a positive value. Now, algebra-wise, I haven't looked at the graph yet, right? Algebra-wise, do some solving. If it's 12 minus x, no, I don't know what you guys would have done. I just subtracted 12 negative x greater than or equal to negative 12. How do I deal with the negative x? What do you guys multiply or divide? Divide? And either or, right? So if we divide by negative 1, this becomes x. Negative 12 divided by negative 1 is positive 12. And what happens when we multiply or divide by a negative? Greater than or equal to becomes less than or equal to, yes? So without even looking at the graph, I think my domain is going to be x less than or equal to 12. So that was me setting the whatever is under the square root less than or equal to 0. Now, my recommendation, it doesn't hurt to graph it also. And I know some of you, Dayton was talking about just wanting to do the graphs, and that's a possibility too. Okay, and I graph mine on my 10 by 10 screen. It goes off the screen, doesn't it? But this 12 gives me an indication. So if I change my window settings and just make my x max, I'm going to make my x max something bigger than 12. Okay? So if I change that to, say, 15, and I regraph it, now you get a whole view of the image, don't you? Okay? And if I just sketch it up here, you have a graph that looks like it's doing something like that. Okay? What graph is this, guys? Combining lessons on you. What graph is this? Is this one of our 12 graphs? Is the square root of 12 minus x, but what is one of our basic graphs? Square root of x, right? The square root function, normally on the square root function, it does what? It starts at 0, 0, and it goes out there, doesn't it? However, the 12 has moved at 12, the negative has reflected it, and so that's what this graph is. Now, I'm going to take that red one off there so it's not confusing. Okay, x values. As we read left to right, my graph is going infinitely off the left side, isn't it? So that supports the less than or equal to. Does this 12 make sense? And if you trace on there, so if I trace all the way over to the right, like Dayton said, 11.96. Again, 11.96 value. And then once it goes to 12.15, I have a blank. So what does that make sense this is? That makes sense that this is 12, doesn't it? So that supports the x less than or equal to 12. I'm assuming directions say to write our answer in interval notation. Actually, it doesn't even really say, but what have we been doing? interval notation. So x less 3 equal negative 12. Well, we started over here at negative infinity, right? Negative infinity always uses a parenthesis. And where does my graph end? It ends at the x value of 12. Remember, domain is always in terms of x's. Is that 12 a parentheses or a bracket? A bracket. Because 12 is part of that graph. That is a point on the graph. Okay, does that help a little bit on 5? Okay, 6. Remember, we're talking domain. Issues are radicals and denominators, right? What do we have in this case? We have a denominator. What do we know about our denominator? Okay, we are going to talk about factoring this here in a moment. But hold that thought for a moment. What do we know in general about a denominator, though? It cannot equal 0, right? So whatever your denominator is, it cannot equal 0. So what do we do to actually work with this problem, though? If the denominator cannot equal 0, we set it equal to 0 so we can see what happens here. So I'm going to set x squared plus 3x equal to 0. I want to know any place that this denominator equals 0. How can I factor this?
Factor of x.
Yeah, there's a GCF of x. Okay, so we can factor out GCF of x. Remember, put the x out front. X squared divided by x leaves me with x plus 3x divided by x leaves me with 3. So x times x plus 3 equals 0. What do I do? Two pieces multiplied to equal 0. I can set them each equal to 0. I just taught this in my Algebra 1 course. Okay, I haven't taught that at beginning for the years, but I just taught it in Algebra 1. So x equals 0 or x plus 3 equals 0. So what is this saying? X cannot equal 0, and what else is it saying? X cannot equal negative 3. Okay, that's what the algebra is showing me. Now, before I even look at the graph, I don't know, do you guys think about this on a number line at all? If I just think about this on a number line, key numbers are 0 and negative 3. And what did we just say? X cannot equal 0. So that's like an open circle. And x cannot equal negative 3. So that's like an open circle. Are there any other exceptions? No, we don't have square roots. We don't have anything else. So the idea here is that, okay, my graph can go left from here. It can be in the middle of here. And it can go right. What's going to be around the negative 3 and 0? When we do this in interval notation, it's going to have what? Parentheses. Because we can't include negative 3 or 0. So, now, did you graph it? Either use your fraction bar. If you don't use a fraction bar, make sure you put x squared plus 3x in parentheses. I'm going to do a zoom 6 because I just had my zoom differently. Aha. Okay. So I'm going to use Dayton as the example on this one. Dayton wanted to know, can I just use the graph? I feel like we'd miss something if we just use the graph here.
Yeah.
Okay. And so this is why it is important to think about it algebraically also. Okay? Because, so if you guys have looked at the graph, you see a graph going something like this, right? And something like that. Now, first of all, what do we know is happening over here at the left? There is an, what are we going to call this? Okay. I hit the eraser instead of accidentally here. Okay. There's an asymptote here, yes? How do we figure out where that asymptote is? Well, if you've done the algebra with me, we know that asymptote is at -3. If you didn't do the asymptote, can you trace it and figure it out? I think you can. Now, interestingly enough, this would help Dayton's case. I just hit trace on my calculator, and it brings up 0 blank, which means what's going to happen right here? There's a hole. So in this case, if you caught that, Dayton, and realized, oh, hey, that represents a hole, because it's x equals 0, my y value is blank, you could have survived. You see what I'm saying there? But if it's not at 0, you're not going to necessarily catch it. So as I trace, as I go left and up, I get -2.87, and I'm up at 8.25. Well, then the next thing I know, I'm at -3.03, but I'm down at -33. So at what? I jumped over the asymptote, right? And when I jumped over that asymptote, I jumped over the whole number, -3. Kind of like earlier, you know, when we talked about 11.96 versus 12. I need the whole number there. I need you recognizing it's that whole number. I need you recognizing it's that.
So what if I do it like one like this, and then 0 isn't a whole number? Does this just keep going?
Yeah.
So I could.
I mean, yeah, it depends on the situation. What happened here, I don't know if you guys caught this, when we factored out an x, this x right here would cancel with this x right here, yes? And when a factor on top and a factor on bottom cancels, that creates a hole instead of a vertical asymptote. Does that sound familiar? Okay. And so that's how we would know, you know, this is why the algebra is important on this one. So as I watch my graph over here, this graph going off to the left is -infinity. As you look at your x values, as we approach -3, my y values go way down, but the x value here, we're fighting over here, the x value there is -3. Up here, my x value is -3. We have an issue at 0, and then this goes to positive infinity. So when you write this, -infinity to -3. Parentheses on the infinity, of course. What about -3? Parentheses or bracket? Parentheses because it's an asymptote. U for union because there's multiple pieces. We pick up on the other side of the asymptote, which is still -3, again with a parenthesis. If it wasn't for the hole, we would just go -3 to infinity. But because we have that hole, we have to take a break at 0. Again, it's a hole, so it doesn't touch 0, so I'm going to say parentheses, union, and then we go 0 to infinity. Okay? Does that help a little bit there? I get it. Some of you guys are more comfortable with the graph. Some of you are more comfortable with the algebra. The ideal situation is using them together. Okay? Okay. Would it be good to just go ahead and talk about 7 and 8 while we're here, which is range? Would that be a good topic to just, before we move elsewhere? Okay, now, domain, we read how? Left to right. You're reading the x values. So domain is all about the x. What about range? It's all about the y. So range is all about the y values. Let me write these down real quick. 7 is f of x equals 5 over 5 minus x squared. And 8 is f of x equals 7 minus x squared, right? Okay, guys. On the range, my best suggestion is that you graph it. Okay, that's my best suggestion, is that you graph. So as I graph this first one, 5 over 5 minus x squared. Okay, you have your calculator, right? You can graph it to see what it has. I guess I could turn the Elmo on and put it on the Elmo. I just have it. But mine is not going to be perfect. Okay, if you graph correctly, you got something like this, right? Now, y values, which means we're going to start where? The bottom, right? We're going to start down here. And as we start down at the bottom, where do my y values begin? My graph is going down off the screen. So that means my range starts at negative infinity. Yes? Okay. So now we're going to trace up if we need to, right? Where is our first break in the y values? And it's happening wherever this is, right? That red dotted line I'm putting in, whatever level that is at. Is it at 0? Is it -1? Is it -1/2? You know, what is it at? And this is where I say trace, yes? And run your cursor off to the right. As you run your cursor off to the right, -0.5, -0.3, I'm at -0.1, -0.06. Gave me a random fraction, -0.04. What is that y value approaching? And it is approaching 0. Okay, so that means the first piece of my range is going to be negative infinity to 0. Negative infinity, of course, has a parenthesis. What about 0? It has a parenthesis, yes? Okay. Now, union, because I'm not done with this graph, am I? My y values, they took a break at 0. And then we have this gap here in the middle, don't we? We have this gap right here, if you will. Like that's a big gap, isn't it? Where there's no y values used. Where do y values pick back up? We need to know what that level is right there, don't we? So I believe when you first started tracing, or if you redo your graph and hit trace, it'll probably pop in right there, won't it? That is also a minimum, if you want to find the minimum. What y value did you guys think? Where do we start here? a y value of 1. Okay. 1. And then where is the next key point? Positive infinity, right? Because my y values just keep going up. So we're going to say 1 to infinity. I got the parentheses on the infinity for you. What about the 0? A bracket? Because the difference is, this is a point on the graph, right? This is a minimum of that parabola. My graph goes through the point 0, 1. So that is a bracket. That's your range. Number 8 should be a little easier, maybe. And I know you guys probably already graphed these, my guess, but 7 minus x squared. Can you tell me what that graph is going to be? In general, you see an x squared, what should your brain think? That's a parabola, right? The negative x squared is going to make it an upside down parabola, and that 7 is going to move it. In this case, it's a positive 7, so it moves it up 7. So when you are looking at the picture, and again, I'm drawing it on here just because it's easier to, oops, what am I doing? Oh man, I can't handle that. Well, that's a little bit better, but oof. Okay. Okay, range, y values. Where are my y values going here? Negative infinity, yes? My graph is going down off the screen, so it doesn't matter whether you think the left side or the right side. We're going down off the screen, negative infinity. Now, whether you go up, left, or right, where's a breaking point or a stopping point? The next point of interest is going to be that point right there, yes? What is the y value at that point? And it should be 7, yes? You can trace up there to find out. Actually, when you first put trace, your calculator tends to put you on that y-axis, so it tells you 0, 7, doesn't it? Okay. So, we just have one piece here, right? No breaks or anything, just one nice parabola. What kind of range are you thinking here? Negative infinity to 7, and 7 is a bracket. I agree. Okay. Sorry. I know Whitney didn't ask range, but domain and range go nicely together. It's a good thing to go over at the same time. Okay. Move along. You guys got other questions you want to ask? You got any? 19? 19. Okay. Realize that it's supposed to say 17 times the cube root of x, right? Now, determine it. I didn't catch the word algebraically being in there. That shouldn't be in there. The idea here is determine whether the function is even, odd, or neither. Okay, so even, odd, or neither. Now, kind of like earlier when Dayton was asking about domain. Okay, you can do the algebra. You can look at the graph. I can be content with either or. Okay, I don't have to have the algebra. You don't have to use the graph. To me, it's another thing I like to use hand in hand. Now, as we go through this, do you guys remember the rules here? It's even if what is true. Okay? If it's symmetric across the y-axis, or what's the algebra rule? F of x equals f of negative x. So those are your even options, right? Okay. What are my odd options?
Negative x equals negative f.
Okay, f of negative x equals negative f of x, or symmetric across the origin. Okay, and we're working on memorizing all these definitions, right? There's a lot, I know, which is, you've got lots of time though. Okay, so let's look at 19. F of x, so let's start by finding f of negative x. I do want to talk about the algebra on this one, but then we can look at the graph, okay? F of negative x says every place you see an x, you replace it with negative x. So I'm going to write this as 17 times the cube root of negative x. Now, here's the trick that is catching people. Okay. This cube root of negative x, what is that number in front of the x? What is the coefficient of the x there? It is a 1, or specifically a negative 1, yes? So if I rewrite that as 17 times the cube root of negative 1x, we can't take the cube root of x, can we? However, can we take the cube root of negative 1? First of all, can we take the cube root of 1? Can we take the cube root of 1? Yes, because 1 times 1 times 1 is 1, right? So side note here. Cube root of 1 is 1. Can we take the cube root of negative 1? Negative 1? Because the cube root of a negative is a negative. Because if you remember, so negative 1 times negative 1 is positive 1. Times another negative 1 is negative 1. So cube root of negative 1 is negative 1. So all of that, what is my point here? The cube root of negative 1 is a negative 1. And so you can think of this as a negative 1 out front times 17 cube root of x. Or in other words, negative 17 cube root of x. Now, so the question I always ask myself now, is this even? Does f of x equal f of negative x? No. Okay? I mean, we have this. We don't want to lose it here. But right now, what I do know is it's not even. And it's not even because f of x does not equal f of negative x. Okay, so what do I find next if we're doing this algebraically? We need to find negative f of x. And what's negative f of x do? We multiply the entire function by a negative. So that means I'm going to multiply a negative times 17 cube root of x. Well, 17 cube root of x, how many terms are there? Is there anything added within 17 cube root of x? No, that is one term. And so when I multiply that by a negative, it's just going to, the negative is going to stay out front. It's going to be negative 17 cube root of x. The only way you distribute that is if there's multiple terms being added or subtracted. So, with that in mind, negative f of x is negative 17 cube root of x. What do we know now? If you haven't already looked at the answer key, you know that this is odd because f of negative x equals negative f of x. Okay? Now, did you guys check out the graph? First of all, do you remember how to do a cube root? It's in the math menu. So if you just go down to the math menu, go math, and the number 4 is a cube root of x, or a cube root, and I can put an x in there. This graph is not a good graph to use for even and odd, is it? It looks like a little line on either side, doesn't it? It's not a very good visual at all, I'm sorry to say. Because when you get that initial graph, it just looks, you can't really tell what's going on. It just looks like there's something here and something here, doesn't it? Now, with just that little bit of knowledge, though, you can already say it's not even, yes? Because this does not look symmetric across the y-axis. Could it be symmetric across the origin? It could be. Okay, and that's what the odd is. I don't know, what worked? Did anyone get a decent graph? Zoom in does not do much for me. Unfortunately, my calculator's taking forever to graph this. What's a zoom fit? Did anyone try that? Okay, zoom fit gives me something pretty helpful, which is option 0 on your zoom menu. It's underneath 9. Zoom fit gives me an option that looks something like this. I don't know if that connects there or not. But what are we doing? Does that make it more obvious that it's symmetric across the origin? That green one? Because if I take that and I reflect it across the x and down across the y, or vice versa, down across the y and down across the x, those green pieces are going to match. Okay? So, for multiple reasons, have I proven to you why it's odd? One way or the other? Okay? Yes?
What's the origin again?
What?
What's the origin again?
The origin?
Yeah.
0, 0. Yeah, the origin being that 0, 0 there. So when we say symmetric across the origin, I kind of think of it as a diagonal symmetry. It is equivalent to 2 reflections, so like a reflection across the x and a reflection across the y. And that's just where I just try and think about, okay, if I take what's in quadrant 1, and if I reflect it across the y, then it's going to look something like that. And then if I take it down across the x, oh, hey, it matches right here. Okay. It is also equivalent to, I believe, 180-degree rotation. If I take this and I rotate it 180 degrees, it's also equivalent to that. Okay. No, it doesn't work. Okay. I had another idea for a moment, but it doesn't work. Anything else in that even odd section? I know we're about out of time here. Did you guys figure out the others okay? I'll take a peek at those, make sure you've got them figured out. Unless you guys have something real quick, that's probably a good stopping point, isn't it? Okay. So keep working on these, okay? Keep working on these, knowing what you're, doing. Work on memorizing. You've got to know those 12 functions, right? You've got to be able to list them for me, along with their equations. It's very doable. Just don't wait till last minute to try and memorize them. Okay?